Measuring pH. The approximate pH of a solution can be determined by using an acid-base indicator, a substance that changes color in a specific pH range. Indicators, abbreviated HIN, exhibit pH-dependent color changes because they are weak acids and have different colors in their acid and conjugate base forms. Bromthiamyl blue, for example, changes color in the pH range from 6 to 7.6, from yellow in its acid form to blue in its base form. Especially convenient for making approximate pH measurements is a commercially available mixture of indicators known as the universal indicator that exhibits various colors depending on the pH. More accurate pH values can be determined with the electrical instrument called a pH meter, a device that measures the pH dependent on the electrical potential of the test solution. We'll learn more about the pH meters in 18.7. How do we calculate the pH of solutions of strong acids and strong bases? The commonly encountered strong acids listed in Table 14.1 include three monoprotic acids, HClO4, HCl, and HNO3, which contain a single dissociable proton, and one diprotic acid, H2SO4, which has two dissociable protons. Because strong monoprotic acids are nearly 100% dissociated in aqueous solution, the H3O plus and OH minus and A minus concentrations are equal to the initial concentration of the acid, and the concentration of undissociated HA molecules is essentially zero. The pH of a solution of a strong monoprotic acid is easily calculated from H3O plus concentration, as shown in worked example 14.7. Calculations of pH in H2SO4 solutions is more complicated because essentially 100% of the H2SO4 molecules dissociate to give H3O plus and HSO4 minus ions, but much less than 100% of the resulting HSO4 minus ions dissociate to give H3O plus and SO4 minus ions. We'll have more to say about diprotic acids in section 14.11. The familiar examples of strong bases are alkali metal hydroxides, MOH, such as NaH, NaOH, and KOH. These compounds are water-soluble ionic solids that exist in aqueous solution as alkali metal cations, M plus and OH minus anions. Thus, 0.1 molar NaOH contains 0.1 molar Na plus and 0.1 MOH, and the pH readily calculated from the OH minus concentration as shown in worked example 14.8. The alkaline earth metal hydroxides MOH2, M equals Mg, Ca, Sr, or Ba are also strong bases, 100% dissociated, but they give lower OH minus concentrations because they are less soluble. Their solubility at room temperature varies from 30 grams per liter to relatively soluble BaOH2 to 10 to the negative second grams per liter for the relative insoluble MgOH2. Aqueous suspensions of the MgOH2, called milk of magnesia, are used in an antacid. The most common and least expensive alkali earth hydroxide is CaHO2, or OH2, which is used in making mortars and cements. CaOH2 is called slacked lime because it is made by treating lime CaO with pure water. Aqueous solutions of CaOH2, which has a solubility of only 1.3 grams per liter, are known as lime water. Alkaline earth oxides, such as CaO, are even stronger bases than the corresponding hydroxides because the oxide ion O2- is a stronger base than OH-. In fact, the O2- ion can't even exist in aqueous solution because it is immediately and completely pronated by water, yielding OH- ions. Thus, when lime is dissolved in water, it gives 2 OH- ions per CaO formula unit. Lime is the world's most important strong base. Annual worldwide production is approximately 280 million metric tons for use in steelmaking, water purification, and chemical manufacture. Lime is made by the decomposition of limestone, CaCO3, at temperatures of 800 to 1000 degrees Celsius.